I would like to solve some problems in real time, because I think when I come with the Smith charts and all the lines in there, it becomes a little more difficult for people to see. So I'm gonna do it in real time, how we find things on the Smith chart, so you can see the progress. That may slow us down, but I have two problems that I would like to solve. And if we don't finish it today, as I mentioned, and I will email everyone, the lecture for Friday and Monday will be online. I will record the lectures and I will make them available, and then you can watch the lectures from wherever you are, but I suggest you do. There will be problems similar to what I will give in a final. So this is a problem that I gave in a final, in another class, another time. So you will get a sense of how they look and how I would solve them. All right, so just to start with that, I have drawn a lot of things on this one, but if you were to see it and given to you, it's not gonna be given like this. What I will give to you, and then probably I will do it here, is gonna be something like that. I will erase this. I cannot do this here. Well, anyways, I will do it in a different way. There is a way of doing it. I would not have this one here. That would be something that you would have to add. All right. I will not have this one. I will not have this one. So I will not have this one. I will give you everything else, and I will also put the notes just to make sure that if I will allow you to put the notes, everybody's going to do different things. And I want you to be consistent. So I will also have included the notes here, like A prime, B prime, all of this is going to be. So in this problem, it says, first of all, read what I'm going to have in the exam. It says, before you respond to questions, I will have that. Do the following. Draw the figure carefully and clearly. Remember I told you that I want you to draw the figure again? All right, so I'm going to ask you to do that, and I will give points to this, you see? Write all the given parameters and the quantities you have to identify. And outline a plan neatly and carefully on how to solve the problem. I will give an extra 100 points. Extra, I mean, this was last time. This part here is gonna be 200 points for you. All right, as we will, or 300 points. Excuse me. This we said finally it's gonna be 300 points. That was from a different time. All right, so I'm telling you, it's not for you. The points here will be for 300. This is a problem. And I will give you another 100 points for that, because I still keep receiving no figures, engineering figures. I receive cartoons. People, I mean, there is a difference between an engineering figure and a cartoon. An engineering figure, for example, in statics, will be to have, to give you the difference, to have, say, let me erase that, not good. It will be to have, if I had a charge and a conducting body, all right, here, and then charges around, or the line, or the electric field lines, it will be, you know, for example, I will give you an example. If I have a positive charge here, then you know that your negative charges will be much closer to the positive charge, and they will be distributed out here. That's for, and then for a conducting body. And let's assume that the conducting body has something like that outside. So this is the conductor. So the positive charges will distribute equivalently, I mean, uniformly, like that. And then when I said draw the electric field, I mean something like this, all right? So what I receive instead of that, and so forth. What I receive instead of that, something like this. I'm telling you, this is what I received. Which if I were to take it as and that's not in the exam in your homework tools for something. If I were to take that literally, I would say it's wrong. Because the lines are not curved, number one. The lines for the electric field go up. Yes, I can see, that you're not going to be able to draw a full circle and do it well, but the fact that they are distributed here and then here, that is a cartoon. All right, that has some information that is visual, it's not perfect. So in any case, that's why I'm saying I'm going to do that. I'm going to give you extra credit for writing well and for providing, as I did at that time. So I'm just going to prepare you for this. There will be extra 100 points on top of 300, which is going to be your problem. This is a problem. These are extras. I will do that for you. All right. So, and I'll tell you why. I have students who are doing some amazing work. Their figures are perfect. It's like, and then I have students who they get the essence of the problem, but they draw these cartoon things. So it's unfair to the students who have done extra work to give them perfect and then give perfect to the other person who has found the solution but has spent much less time. That's why I want to differentiate on the basis of how the students present it. Okay, so that is what I will always mention this in every problem I'm solving from this point on. So in this case, I have a load, and what do you observe when I give you this load? That I have given it to you in terms of a conductance and a capacitor, all right? And they are in parallel, so you will make those observations later. But I give you the conductance in 1 over O. I give you the capacitor in picofarads. I give you the characteristic impedances of these two lines. And I give you the amplitude of your AC source. And then I give you the frequency. And then I start 5 Z1 and this abyss, so that you have maximum transfer of power to the load. That's one. Find the voltages and currents at AA prime, BB prime. Right? We have that in there. But we'll solve it. How much is the power dissipated by the conductance? And then here I remind you that Vs is not RMS, as a matter of fact. Put this here, it's maximum. It was RMS at that point. Is a maximum. Okay, value for maximum in the 1 millivolt, and then the complex power is given in this form. All right, always the 1 over 2. I'm going to remind. Okay. And so these are the questions. Okay, now what I would like you to do is this. Solution. When I say write what, remember I will give you like 10, 25 points for just writing down. This is what I've been given. Because a lot of times students are asking me about things that I have given already, which means that you have not noticed that I have given those things. So you have to write them down. It's not going to take you very much to write this. What do we have to find? This one, DS and Z1 in 1. In 2, assuming these two, that you know them, you have to find these voltages. In 3, assuming that you know that, you have to find the power, assuming that you know all of these. They're not independent, 3 independent questions. One is based on the other. Of course, I understand that you're going to get partial credit if for some reason you make a small mistake here, it propagates. But if I'm not going to take points for the same mistake, if the rest is correct, all right? But in any case, observations before you start solving anything. Before, you have to understand what I'm giving you in the problem. So to have, so now at that moment, before I start my observations and write things, I'm gonna go to my figure here, and I'm gonna start including specific impedances that are important as I'm solving the problem, all right? So in the first one, say, find Z1 and disabase so that you have maximum transfer of power from the load. Okay, so look at my observation. In order for this to happen, we know, all right, it says here, for the maximum power transfer from the source to the load, we know that the impedance that is presented, right, at is equal to 0. So I have to introduce this impedance. So here, had another one that I erased multiple things. So let me see. So I have to add here. I remove that frequency because I have it below. I have to add here this impedance. And this is the impedance that you see, input impedance at A prime. All right, that's how I add the impedances the moment I need to say something about that. So for us to have maximum power transfer from Vs to the rest of this structure, we need to make the input impedance here equal to 0. Right? That is the first observation. So this is what it says here. So I know how much I have to make this one. Okay. Second observation, and that we are gonna, I want you to keep it in mind. We want to place, therefore, and also it says here, you see, the other thing, I gave you already what I want you to place here and what I want to have as a termination, which is open circuit. These are given. So I am telling you already how to solve the problem. I'm asking you to place an open circuited stub at this point, all right, in series. So that is the problem given. Therefore, my observation is the following. We want to place an open circuited series stub. Series is important. Because it is in series, then what I have to include next to it is a series, is an impedance, not an admittance. All right. So that means that what I want to have here is an impedance. All right. Because the input impedance here, which is then I will show us this. All right. Maybe. Okay. And I have to, yeah, it's a little bit, this software does not help, but in any case, I have to clean it up so you don't get confused here. All right, so because this is in series, whatever effective input impedance I would have from this at this point, is going to be in series with this impedance. All right, so practically, if I were to write down here, after my observation, I can move this part. Here is what I would say. If I were to replace my shunt stub by an impedance, all right, my circuit will look like this. So I will have a transmission line here, then this and this is A prime, all right? And that is connected to the source. I don't change anything about the source, it remains the way it is. And then here it's B prime. Now, where the stub comes into the picture, all right, these are extensions, they're not transmission line extensions, they're just graphical extensions, so I don't put things on top of the other. The equivalent to a stub is going to be a stub impedance. I call it Isabes for stub. And I can express it in the form of an admittance or an impedance, all right? However, because this is in series with the rest of my problem, all right, which in reality, the rest is another transmission line here. All right. And then I have a load at the end. So let me do the load here. And my load, it's YL, which is G plus J omega C. The load, I have given it to you in, with or not normalized, the load I have given it to you in an admittance form, all right? From the units you can tell. However, as I move this load here, so practically this is C prime, this is D prime. So when as I'm looking here, and that's my Z input at C prime, all right, that I have included up here, you see that? That means that at this point, as I'm looking towards the load, the only thing that I see is this Z input CC prime, which means that I could erase all of this. And what I would see here is this one. I could see a Z input CC prime. Now, so practically, I can remove it here because I have already replaced it, all right? So practically all of the line from CC prime to the line to the right, I am replacing it with this input impedance. Now, in reality, I could either use an input impedance or an input admittance, or I can take the inverse of that and then I can have an input admittance, all right? Yes.
Load at the end of the top, your original. If those were changed to impedances, those have to be added as a 1 over G.
Yes. So,
1 over.
yes, yes,
Okay.
of course. But I kept it as an admittance. If you have an admittance at the end, which is the sum of the two, all right, an admittance is the equivalent of an impedance. So you can represent your load as an impedance or as an admittance.
And the way that you have them in series and parallel switches impedance.
That's it. So you can represent that here to solve you can represent your load as an admittance, or you can represent your load as 1 over G plus J omega C. All right, the inverse. Which is equivalent to 1 over Z sub L equal 1 over G plus 1 over J omega C. In fact, excuse me, what did I say? G plus J omega C. All right.
Okay, so So the
Okay.
adding the two at the end, just the values of those two at the end.
It will give you one or wrong. What do you mean adding to G and C?
Yeah, because they're so G plus J omega C.
Yes.
Seems like it would be in series, but if you have those two in parallel, wouldn't you have to add them here? G times.
G is an admittance. And J omega C is an admittance. They are one of their own.
Yes.
So admittance is in parallel sum.
Okay, that's what I was asking.
Here.
Alright.
All right. But it's an admittance. Now, the inverse of this is an impedance. Okay, so you have an option to either keep it like this or use it like that. What makes me decide which one of the two I'm going to use? The fact that I add something here in series. Because I can use my Smith chart either for this or for that or for this. I mean, at the end of the day, I can calculate the value here. And I have a choice, since everything is given, to put it in admittance form or impedance. My advice to you is if you add a stub in series, use impedances on the Smith chart. All right, bottom line, if you add a stub in series, use impedances on the Smith chart. So practically, what I do there is, that's my observation, which I want you to keep it in mind. While I can make that easily and find it, in reality, I'm gonna invert it and get this up there. All right, and at the end, therefore, I'm going to replace my load with an impedance. Why? Because I have to add a stub in series, and it's only impedances that you cannot do anything else on the Smith chart but adding things in series. So a Smith chart, if you want to do the things that we are doing in terms of design, if you have a series stub, you have to use impedances. If you have a sharp stub, you will have to use admittances. And then I will show you how you will do that. All right, so remember it as an observation. And I give it to you so you remember that. A series, since I'm using a series stub, then I will use impedances. All right. And now here it shows why I'm gonna do that, because I can only add things on the Smith chart. I cannot do anything. I cannot do the inverse of something and then add it. No, the Smith chart does simple stuff. All right, so I can only add these two. All right, so now we know that I have introduced Z input. Therefore, my choice is to use impedances. All right, that's my second observation. So here in 3, what I'm trying to do is exactly that. I'm trying to go to my load, all right, to calculate. So now calculate here, it says that I will have to calculate the load. So as a result, 3 is my next step. Move it down a little bit. And as part of 3, I calculate Z sub L, which is practically also the Z at DD prime, all right? You have a choice to call it either Z load or impedance at DD prime. It's the same thing. So I calculate that. I mean, I did that exactly the way I said, all right? I calculated this first, and then I took the inverse, and then it gives me that. So now what I have a transmission line. So here I will do this again for you. So I'm going to take this one, copy. So I'm solving the problem like as if I had to solve it myself, all right? No, cut. That is not good enough. Cut. see, because it's not going to allow me to change it. Copy. Paste. Okay, so here, now that I've done this, I found Z input. I need to transfer Z input at D. So ZL, I need to transfer ZL to C and C prime. So practically, after I made that decision, I'm going back to my original problem. And I'm saying that here now, since I decided to use impedances, now I will have to do one thing first. I have to take my impedance load, which is here, and I have calculated it. And then I call it ZDD prime here, just because it's connected there. All right, I have now calculated, you can see it, what it is. And I have practically to do what? First thing, I have to move that by lambda over 2. So moving things, we use the Smith chart to move. Because when you move from here, from one point of a line to another, which circle do you describe on the Smith chart? How do we call that circle? The constant Vswr circle. Why do we call it the constant? Because everywhere on the line, as I move on the line, the Vswr is constant. All right? So on the Smith chart, if I were to do this on the Smith chart, which I will try to do that here, let me get the Smith chart, move it up. Okay. What am I gonna do first is find my impedance. All right, so I wanna find on the Smith chart, what do we have to do to find it on the Smith chart first? What do you have to do first? To find ZDD on the Smith chart. Can I find ZDD on the Smith chart the way it is? No, I have to do normalize. Therefore, it means that I have to normalize it, which is the value here divided by 50. And therefore, it's going to be, so 39 divided by 50, 39 divided by 50, that makes it 0.78 minus J 48.75 divided by 50. That makes it 0.975. Now we are ready to go to the Smith chart. Okay, the first is the real part. The real part is 0.78. How am I going to find 0.78? So here, 0.78 is somewhere here. You see that? I'm going on the horizontal line and I read where is 0.78. 0.78 is right before 0.8, obviously. And then from there, I write the constant resistance circle. And the constant resistance circle is going to be something like this. Okay, move it a little bit there. And it's not exactly right. Yeah, I think it's perfect. Okay, the constant resistance circle is the one that goes through this point. All of the points on this circle have the same resistive part, normalized. Okay. Now, what else do I have to find out? I have to find the circle that gives me minus 0.975 as reactive part. So I have to go to the lower part of the Smith chart, the lower part, because this is where the negative numbers are. And then I have to find 0.975, 0.9, and I think it's 75, all right? Is it 75 or 57? Yeah. Okay. I never, I always flip the numbers. Interesting. But anyway, 0.75. 5 here, 7 somewhere here, let's say somewhere I would 8 in the middle, all right? So I would go, and in fact, the Smith chart is very forgiving in terms of making small mistakes like that. So I will start from here, and I will draw that here. You have to be a little more careful because I will not be able to do this circle. The circle practically that is one of those, all right, that go there. You could do the whole circle if you want, but you have to go really out because the whole circle would have, it's going to be tangential to this line, and it's going to have center, its axis, it's centered on this axis, so it's a huge thing. So we only, okay, so here. Professor. Hello?
Isn't that 8 points? Or 0.8?
I cannot hear you very well.
I was saying, isn't that 0.8?
It's 0.975, not 0.875. Yeah,
No, I mean where you put it on this chart.
Yes, you're right. So wait a second. I put it in the 0.7, not 0.9. All right, thank you. So it's here. All right, is that what you meant?
Yes.
Thank you. Thank you very much. Oops. Thank you. All right. So now I have to take the intersection of the two here. And I have to remember that this one is, so I always write it here, that this one is my Z input, my ZL, you can write it as ZL, for example, or ZDD prime. Okay, so that is your starting point. Now, remember what we said? We have to move this by half a circle. Now I will do all of this, and then you will see what is the conclusion out of this. So to create the Vswr circle, I have to go to the center of the Smith chart here, use that as a center of my circle, and then use this as the radius. All right, so I will erase extra lines because I don't need them. And then I'm gonna write a circle. Okay, I'll fix it. Okay. All right, I'm good enough. Now, a little more, if you want to be more accurate, that's fine. Okay, and now I have to move on this circle from here. There are two ways of moving from this point. Either clockwise or counterclockwise. Which direction do I move? Clockwise. Why? Because I'm at the end of the line. When you're at the end of the line, there is only one way to go, and it's towards the source. All right, so we're gonna go like that. And we're gonna go like that until when? While I'm doing this, and I suggest that you always use these arrows to show which way you're going, very important. Tell me then, where am I gonna stop? The line that what? Yes. So what your colleague said is that I have to find the circle that takes me to the center of the Smith chart. And the only circle that takes me to the center of the Smith chart is this one. Let me use a different color. The only circle that takes me to the center of the Smith chart is this one. All right, and so forth. I'm not gonna draw the whole thing because I don't want extra lines. So I'm gonna stop. I'm starting at this point and then I'm gonna stop there. If I would do that, if they had not specified the length of my line. But in the problem, they're specifying the length of my line. They tell me that this one has to be half a wavelength. So I don't have a choice. I have to move by half a wavelength. So I'm not going to stop here, all right, which I would normally do if I had a flexibility. I'm not going to stop there. So I'm going to continue until I describe half a wavelength. Now, how do you pay attention to how far you go? If you want to see how far you travel on the line, practically you will have to connect the center of your chart. All right, you connect the center of the chart to your point. This is your starting point. This is where you start. All right, and you go like that. Okay. Now, where do you measure your distance? You measure your distance here. So if I'm gonna go half a wavelength, if I were to stop there, I would have to go around here like this and stop somewhere there, but that's short of half a wavelength because you remember from here to there is a quarter. All right, from here to there, half a circle is a quarter of a wavelength. So the full circle is half a wavelength. So if I were to go around by half a wavelength, where am I gonna come to? I'm gonna come to the same point where I started. Okay, so do you remember what I said? That every time you travel on a transmission line by half a wavelength, the impedances repeat themselves. So I did not really have to do that, but I wanted to do it so I will remind you how to get the impedance and how to move around. But practically half a wavelength, if I knew this, I would not have to go to the Smith chart for that. I would say immediately, okay, if I know ZDD prime, my impedance at CC prime is identical. So then, in fact, if you don't remember that, then do the Smith chart, but remember, which I hope you will remember, but make sure that as you know how to go around the Smith chart, all right? Because if you do it correctly, you're gonna find the right result, even if you don't remember. So in any case, what you find is therefore, the result from this effort is you conclude that your Z at CC prime is identical to Z sub L or ZDD prime. I write both of them so you remember it. These two are the same, okay? It's equal. So I know how much ZCC prime is and how much is it? ZCC prime is practically, what did I say? We found it here, 0.78. 0.78 minus J.975. Oops. .975. Okay. So I don't have to do that. But if you don't remember that half a wavelength gives you the same impedance, do it. So this one is what gets you. Now, I therefore, let me add one more page here, add page. Okay, so, and I add it down there. Okay, so now I'm taking this one, copy, put it here, paste. And I said that now that I found that this ZDD prime is the same at CC prime, I can erase this part totally. I can erase it. Does not exist for me anymore. And then I place here my ZCC prime, which is 0.78 minus J 0.975. Okay. Now here I have lambda over 4 and Z1. And then I have to find Z sub S, which is the impedance for the star. All right. I'm looking at this. What does this remind you? A quarter wavelength transformer. When you see a quarter wavelength, it's not there accidentally. All right, nobody's going to give you a quarter wavelength just because they like the number. They will give it to you, especially when they allow you to have an impedance, different impedance from zero. So that is my quarter wavelength transformer. That's what I observed. So my other observation is that the line, transmission line from A prime to B prime is a quarter wave transformer. And therefore, what do I need to do to be able to use it as a quarter wave transformer? You remember that one of the conditions, the quarter wave transformer only works if the load here is real. All right. So that implies from here that the combination of these two impedances has to be real. That implies that Z input at B prime, which in fact I'm going to see it from here rather, it has to be real. Otherwise, I cannot use a quarter wavelength transformer, which then means, that my ZCC prime plus ZS, normalized, all of this, it has to be real. What does that make me believe? That implies, first of all, that ZS, what do I know about ZS? Can ZS be real for a star? No. As we know, ZS is imaginary. Therefore, we want ZS to be equal to J 0.975, because this way, if ZS normalized is 0.975, then the sum of the two becomes real, 0.78. In this case, therefore, if that happens, then my ZCC prime becomes 0.78, which is real. So if I manage to make Z sub S this one, then I'm done. Okay. How am I going to make this? Now I can go to the Smith chart. So in the Smith chart, I can, at this moment, I will keep this as a matter of fact, because I want you to have it, but can I copy this? Copy. And then here, I'm going to add another one. Okay. Add. Oh, okay, maybe I said double. It is duplicate. Paste. Okay. Okay, perfect. It's still learning how to do this thing. Okay, came to the right place. All right, so I'm going back to the Smith chart. I use the new one, all right? I mean, you can use the same Smith chart, but for me to clarify it as you practice, I'm gonna use a new one, but you can use only one, all right, for this. Where do we go if we want to plot? So here we have to solve for the stub, all right? So the Smith chart here is to calculate the stub's length. That's why I'm coming here. Because this is the only one which is going to give me the input, normalized input impedance that I want, all right? So what do we know about the stub? The stub is open circuited. Remember, we said that? Where is open circuit? So first of all, I make that stub is open circuited. Okay. Where do I go to find an open circuit? Does not matter. Open. Open circuit is an infinite impedance, which means I'm going to go to this point, which is infinite. All right. So I'm going to go here. And this is going to be my Z, oops, excuse me, open circuit. That's the open circuit. Remember, the stub was like this. All right, and then we had a transmission line here. That was the stub. All right, and it was open circuited here. When I use this one, it was too thick for this. That means open circuit. All right, and we want to find this length. So we start with the open circuit, and I'm moving this way on the line, on the stub, all right? So now I'm starting at the open circuit, and I'm moving which direction? Towards the generator, because I'm at the end of the stub. There is no other way to go. So I'm moving this way, all right? And I will have to move until where? Until I find that my input impedance here is J.78. Do you agree? Yes, thank you. I was thinking the real part, 975. Yes, until it's 0.975. So I know that I'm gonna be on the upper. So I will have to move all around, and because I started here where you see the open circuit, I'm going to move like this here. And I will move like this until I find a positive 0.975, which in fact, I have ways to go. That tells me that the stub is gonna be a little longer, but that's okay because somebody specified that it has to be open, right? So you go like this on the same line where you found. This is the circle for the imaginary impedances that don't have a real part. So you go on this one until you find 0.975, which is here. And that tells you that you have to travel this much to find this one, which is your Z sub S normalized. All right? I have to travel this much. Now I need to find out how much I had to travel because that's going to be the length of the stub. So how did we say we do that? We connect the center of the stub of the circle with the starting point. That's one. And then with the end point, we draw these two lines. Okay. And then we measure, we go on the outer here. We go around because that's where we measure distance on the outer circle. And we go around until we stop there. Okay, so now how do we count? This is 0.25 and this is 0.5. So there is a quarter of a wavelength that I have already done by coming here. And then, so I keep that in mind. So from the lower part of the circle, from here to here, this is 0.25 already. And then from here, all right, from the beginning, because it goes back to 0 here. From here till there is 0.122, 0.13. Okay, it's 0.123. When I stop there is 0.123 lambda. So I have now to sum the two. All right, so the total distance D sub S for my stub is 0.25 plus 0.123 lambda. There. Okay, which finally gives me 373, yeah, 373. Lambda, and that's D sub S. So here you have found D sub S, all right? So now I know that if I make the length of my stub here, if I make that D sub S, if I make D sub S 0.375, I think, 373, thank you. If I make it like this much long, then practically the input impedance here will cancel the reactive part of the input impedance there. All right, so the sum of the two is going to be real. And the sum of the two, therefore, now we are coming back to the quarter wave that we had, but we continue since we found the stub length. And we say, now that I have found the stub length, so from below, we found from Smith chart below, we concluded that D sub S was 0.373. 73 lambda. So that is important because it's one of the parameters that we need to provide, all right, to the solution. And then from here, now we can go back to our problem and say we have the quarter wavelength transformer. In fact, I'm going to take this one. This is very analytic. I'm not going to ask. In fact, you did not even have to do all of this. I'm doing it so it just reminds us how to do specific things. Duplicate this one. Come here. And then practically here now, what do I have? I have an impedance here, which is normalized 0.78, but if I am, which is in fact here, is the Z input at BB prime, that's the impedance, which is 50 times, I denormalize it now, all right, 50 times 0.78, which in fact makes it, I need to finish that and we are done practically here. 50 times 0.78, which makes it 39 ohms. So the final step is to calculate Z1, which is the square root between 50 and 39, which in fact gives us 50 times 39 square root 44 ohms. So now you solve the problem. This is how the extensive solution, but for somebody who has already numbers like that, you don't have to go to the Smith chart to know that half a wavelength gives you the same impedance. All right, so practically with half wavelength, you can come here and immediately say that is going to transfer here. And then from here, immediately say this is how much I want this to be. And use only one Smith chart for this and then do the other one. All right, but I did the whole thing today, so you can see how much this is. I'm not gonna try to do every step like that because it's gonna be impossible to solve many problems, but I wanted to use this example today because a lot of students, I have to say, ask me how to travel on this, how to do, please read those stuff, read it, because everything builds on the past. And if I have to explain everything from the beginning, we will never be able to solve another problem, all right? So I did this today, so it is on record. I'm going to put this, as a matter of fact, as well as Mondays on Canvas for you to go through and see how we did this problem, all right? Okay, thank you. I will assign to you an exercise today. So check for it. It's going to be similar like the other one. Make sure that you, I will do it right now. But as you leave, make sure that you do the exercise for Friday.
Are we ever going to have a stub that has the characteristic impedance that's not?
No, not in this class, but in practice, yes. And usually that it depends on the layout of your circuit. But in this class, no.